Hello everyone, welcome to the lecture series on Fundamentals of Generative AI Large Language Models. We are in the week 3 and in this particular session we will be looking into one of the most important concept called reparameterization trick. This is very important and then this will give the complete intuition why so far we have never seen the architecture of VAE. Towards the end of this particular session, you will see the architectural diagram of VAE. Although we have seen the encoder, decoder, then we have seen the loss function, but we will be looking in detail and by end of this you will be getting an architectural diagram. So, this we have already seen in our previous session that this is the loss function of VAE, which has totally two components. One is we have an reconstruction term and the second is regularization term. What exactly is a reconstruction? Now, if at all if we have an continuous data, then this particular first term will be taking a mean squared error. Suppose if we are taking an binary data, then the first term will be an binary cross entropy. So, basically this particular term will tell us how far the reconstructed data will be similar to the original input. So, that is what is the first term. Second term what we have is the regularization. What is regularization here? It is a KL divergence. Now, KL divergence since both of these are Gaussian distribution in a closed form, the KL divergence is written in this particular form. So, now what exactly KL divergence this particular regularization term ensures that the encoder distribution remain closer to the prior distribution. Now, what exactly is the problem here? Now, when you look into the entire loss function, we have somewhere Z. Now, Z is sampled from this particular distribution. What is the sampling here? We are randomly picking one value from this particular distribution with the parameters mean and variance. Now, when Z is randomly sampled, then there involved an random operation. So, since sampling is a random operation, always randomness breaks the gradient flow. If there is no gradient flow, then how do we compute the backpropagation? How do we update the parameters? Therefore, it makes the backpropagation impossible. Now, the question is the solution for this particular one is a reparameterization trick. And what is the question? How do we compute the gradients when part of the network involves a sampling? Therefore, we require this particular concept called reparameterization trick. So, let us get into the details. Now, we will be going very slowly, we will be looking into each step. So, towards the end of this particular session, you will have a complete clarity. Now, what is seen here? There is an input. When input is passed to an encoder, what is that encoder will give us? Encoder outputs the parameters. What parameters? The parameters of an appropriate posterior distribution, which means encoder is going to give us this mean and then the variance. Then once we get this output, what is that we are going to do? What is the next step? By now you should be able to answer to this. So, the next step is Z is sampled from this particular distribution. How is that? You will be writing mathematically. Z is sampled either from this or the Z is sampled from the parameters from this distribution. So, both are the same. So, once Z is being sampled, what is the next step? So, you will be passing a Z to an decoder. So, Z is which is a latent space Z is then passed to an decoder. Now, once we pass Z to the decoder, what is the role of a decoder? Decoder has to reconstruct, it has to give us the output, and that output we call it as a reconstructed one, or we say that decoder has generated the data. Mathematically, how is that you will be writing it? So, x hat is the reconstructed data, right, and to that Z is passed as an input, and here f of theta here is an the decoder neural network. Therefore, when we see Z is a latent vector and then f theta is the decoder neural network, and theta here represents the decoder decoder parameters. These decoder parameters are weights and biases. Now these are the learnable parameters. So once you update these parameters, definitely x hat, whatever is the reconstructed value, becomes closer to the original input. Yes, therefore x hat is a reconstructed output which is produced by the decoder. What is that we are seeing in this particular slide? We are seeing the feed forward process. Input is passed to an encoder. Encoder is going to give us the distribution parameters. Then Z is sampled from this distribution. Then Z is passed to an decoder. Decoder is a neural network which takes Z as an input and produces the data, which is x hat, denoted as x hat. Now whatever are the decoder parameters, theta, these are the learnable parameters. So once this is done, what should be our next step? The whole idea here is to see whether we can able to compute the back propagation. So let us now see what exactly is going to happen. Now, when Z is passed as an input to an decoder, and decoder, if input is an tabulated data, then we can imagine that encoder decoder can be a simple multi-layer perceptron. So now let us assume the decoder here is a multi-layer perceptron model. So Z is passed as an input to the decoder. Now what is that the decoder has to give? And how is that the process is going to happen? First, you are going to, when Z is passed to an first hidden layer, which we denote it as H1. How is that we perform? Z is passed as an input, therefore Z gets multiplied with the weights. Let us assume those weights are denoted by W1, and you will be adding the bias term B1. And since it is a hidden layer, we will be also using an activation function, and that activation function here is ReLU. So that is what is been written here. So what exactly operation has taken place? The decoder takes the latent vector Z, multiplies it with the input weight matrix W1, and then add the bias B1. And then what is that we are doing? We are applying the activation function, and here the activation function used is ReLU. Therefore, H1 is the first hidden representation inside the decoder. Okay, so once you pass Z to the hidden layer, we are going to get the output. Now that output will be passed to the next layer. So here the next layer is the output layer. So how is that you will be passing? What is that we are passing? Here the output is denoted as H1. This H1 will get multiplied with that particular weight matrix, and then you will be adding the bias, and definitely there will be an activation function there as well. So is it not the equation is written in this way? So H1 gets multiplied with the weight matrix W2, and then we are adding the bias. Now that entire you will be passing it to an activation function. So what activation function? What is F here? That primarily depends on what kind of data we are reproducing, right? So how is that you are doing? H1 is the hidden representation that is passed to the next layer. Which is the next layer here? It is an output layer. Primarily for what? For reconstructing the input. Now here F is an activation function that primarily depends on what type of data that we are trying to reproduce. So here the possibility is either you can have a continuous data or you can have a binary data. Suppose if it is a binary data, we will be using a sigmoid activation function. If we are using a continuous data, then we will be using a linear activation function. So far this is fine. Now what are the learnable parameters here? Is it not W1, W2, B1 and B2? Therefore, at the decoder side, the parameters are W1, B1, W2, B2. Now, once we get the output, what is the next step? What is the next step? Can you recall? the next step is to compute the loss. So once the output x hat is obtained, we will be computing the loss. Now I am writing very generalized representation here because that loss depends on either it can be a mean squared error or it can be a binary cross entropy. So we will be computing the loss, and the loss will be between x hat and x. Once we compute the loss, what will be the next step? You have to update the parameters y. Initially the loss value will be high, then we will be updating the parameters, then over a period of time the weights we are going to get the optimized and the bias will be an optimized one. So once x hat is obtained, we have to compute the loss, and that loss will be between x hat and x. Then we will be updating the parameters. Now, if at all if you want to update the parameters, somewhere from our week 1 go back and then recall what is that we need to do. We have to compute the gradients, right? So how is that we compute the gradients? So first we compute the gradients with respect to W2 and B2. Right. So how is that we can write this particular derivative? If you want to find out, is it not derivative of loss with respect to W using a chain rule? Is it not first you will be computing with respect to x hat, and from x hat we can reach to W2. So is it not we write in this particular form using a chain rule? So derivative of loss with respect to W2 will be loss with respect to x hat and x hat with respect to W2. Similar way even the bias term. So derivative of loss with respect to B2 will be derivative of loss with respect to x hat and x hat with respect to B2. So this is with respect to the output layer. So from here you can able to compute all of these values. There is no problem. Now further if we go back, further going back is reaching now to hidden layer. So at hidden layer, what are the parameters to update? Is it not W1 and B1? How is that we will be reaching using a chain rule? Is it not a derivative of loss with respect to W1 and derivative of loss with respect to B1? How is that we compute? It is the derivative of loss with respect to x hat, and from x hat we reach to h1, and from h1 we reach to W1. So is it using a chain rule, is it not this is the form equation? If you want to update the weight W1, the path during back propagation, the path is first you will be reaching to x hat, and from x hat you will be reaching to h1, from h1 you will be reaching to W1. So this is what is the chain rule. So here also we can compute values for each of the term. So therefore can we say that the gradients with respect to the decoder parameters W1, W2, B1, B2 are all computed using a standard back propagation. Hence, in VAE or in a standard VAE, decoder side is not a problem. So this is what we have reached. So till where we have computed the gradients? We have computed the gradients only till the decoder part. So now let's proceed to the next step. So I hope up till decoder it is clear. Now what is the role of a decoder? Decoder has to take an input Z, and then it has to reconstruct the data, or it has to produce the output, which means whatever the output that the decoder is produced, is it not from Z only? So then the loss whatever we are getting definitely depends on Z through that x hat. Right? Are you getting this? Now if at all if you are computing the loss, and if the decoder has produced the output, that output has come by taking Z as an input. So which means the loss depends definitely on Z as well. So now we are computing that particular using a chain rule. So what is that we have mentioned here? Since a decoder output is produced from Z, and this is the mathematical equation, then definitely loss depends on Z through x hat. How is that? We will be computing now this derivative of loss with respect to Z. Is it not using a chain rule? Derivative of loss with respect to Z is computed as loss with respect to x hat, and from x hat we can reach to Z. So, this is how we have computed the derivative. Now, you can ask how we are computing. Once you sample Z from that particular distribution, is it not Z is just a numerical numbers? Is it not a vector? So, from our session, all the sessions we have understood. So, Z is sampled. Once you sample, it is just one numerical number. So, definitely that is what is written here. Since Z is treated as a numerical input to the decoder, definitely the decoder is differentiable with respect to its input. Therefore, we have reached successfully the gradients back from reconstruction till this Z. So, I hope this is clear. What is that we have done? Our entire aim is to ensure that we can able to do back propagation or not. Somewhere in the first slide we have seen that back propagation is difficult. Now we are trying to understand why that difficult, where is that difficult. So we were able to reach till Z very successfully. Okay. Now with this let us try to understand further. However, the difficulty is not in the decoder, we have understood. Now where exactly is the problem? The real problem starts when you you want to now pass the gradients from Z backwards. So back to encoder parameters. So what are encoder outputs here? The encoder outputs are mean and variance. Later the variance is converted into standard deviation. Okay. So the encoder outputs are this mean and standard deviation. Okay. Now you have to compute the gradients with respect to these two. Now let us see whether we can able to do that or not. So during the back propagation you have to reach until the encoder parameters. So we are successful reaching till Z. From Z now we need to update, we need to compute the gradients with respect to mean and variance or mean and standard deviation. So we are now somewhere seeing that there is a problem here. So let us see how do we pass the gradients from Z back to the encoder parameter. Now, but the problem starts when you try to update these parameters. Now, let us try why this problem has occurred. So encoder is producing a mean and variance or mean and standard deviation. Okay. Once it gives this, how is that we are getting a Z? Is it not Z is sampled from this particular distribution? Okay. Now, so we have understood that till Z you can able to back propagate it. Then encoder is giving these two parameters and Z is sampled from this particular distribution. Now, what is that we need to do? We have to update these encoder parameters, right? Now, in order to update these encoder parameters, we need to compute the gradients with respect to mean, we need to compute the gradients with respect to standard deviation. So using the chain rule, can we write this? So now you want to compute the gradient of derivative of loss with respect to mean and derivative of loss with respect to the standard deviation. So now we need these two. So using a chain rule, can we write in this way? How do we reach from loss? How do we reach to this point during a back propagation? From loss, can I reach to Z, and from Z can we reach to this? Now how will we reach till Z? It is already written here. So using a chain rule, we can reach till that Z, from Z we can reach to mean. So this is how you reach to mean and this is how we reach to a standard deviation. So I hope up till this particular point it is clear. So what is derivative of loss with respect to Z? This is the formula. Now the problem comes here. These two are the terms. Now you need to compute the derivative of z with respect to mean, derivative of z with respect to standard deviation. We want these two terms values, we want these two. Now can we able to compute this? What do you think, what is your answer for this? Definitely no. Why it is no? Because z is sampled from this distribution. When it is sampled, it is a random operation. Therefore, whatever z equation that we have written, it cannot be directly expressed as a differentiable function of mean. You cannot differentiate with respect to this. This is the problem. I hope this is clear to you. What exactly is an issue? We want to compute the backpropagation. Now, in order to compute the backpropagation, up till z it is fine. From z, when we backpropagated further to update mean and variance, we are seeing that there is a problem. What is the problem? Using a chain rule, we can able to reach up till this point. But we know this value, but we doesn't know these two terms. Why we doesn't know these two terms? Because z is sampled from this particular distribution. When z is sampled from this distribution, z is not directly expressed as a differentiable function of mean and sigma. Therefore, there is a problem at this point of time. Direct backpropagation through sampling is not possible. So, because of this particular, we require a concept called reparameterization trick. Now, let us see how, if this is the case, how do we sample z so that we can compute the gradients. So, z is a problem because you have sampled z from a distribution. If that is the problem, how do we sample z? So, can we think in this way? Instead of directly sampling z from this particular distribution, can we express z in this way? Can we do sampling operation? Can we write z in this particular form? Now, if you look into this from our session, the encoder is going to produce these two parameters, that is mean and then the standard deviation. Now, once it is going to give us these two, which means, look at this, is it not here whatever are these two terms, that mainly depends on our input x and then the encoder parameters weights and bias. Agreed? Yes. Then look at the next term, we have this epsilon. So, what is this epsilon? From this equation we are seeing that epsilon is something which is totally free from that mean and variance, mean and standard deviation here, and epsilon value is something which is sampled from normal distribution or Gaussian distribution. So, now you can ask the question, when encoder is already giving us a mean and standard deviation or variance, why is that we require this epsilon concept? So, why do we require this epsilon? Now, do you agree to this? For a given input x, there exist multiple such z's, but here if you write an equation z in this particular form, then mean and variance whatever the encoder is giving, from that if you want to generate a different z, then there has to be some randomness. That randomness is what is this epsilon giving us. Now, but at the same time, now you can ask the question, ma'am, again there is a randomness here. Yes, there is a randomness, but it is completely independent of that mean and then standard deviation. So, you see here whatever the epsilon is something which is not learned by the network and its value is being sampled from this particular distribution. Therefore, the network does not learn the epsilon and it is completely independent of the mean and then the standard deviation. Therefore, during a backpropagation, it is randomly picked one value, which means it is just one number. During backpropagation, can we assume this to be a constant? Right? Yes. So, therefore, now whatever z that we have written, z is now differentiable function with respect to whatever are the two parameters, mean and then the sigma or standard deviation. This is reparameterization trick, one of the most important concept. Let me quickly summarize to you what exactly we have discussed. See, encoder is something which is giving us the two outputs, that is mean and then the standard deviation, or mean and variance. Now from mean and variance, when you so far what we were doing, we were sampling Z from that distribution. Now when we were sampling, there is an randomness here, because randomly you are picking one value. Each time you pick, the value is different. That different value, when you pass it to decoder, you get a different reconstructed one. Second time when you sample it, again you get a different, then you get a different variant. So, but the problem is backpropagation is causing an issue. Why backpropagation is causing an issue? Because Z is sampled in this way. So, can we sample Z in a slightly different way? Okay, what is that different way? Z is sampled from this particular distribution. That is, Z is sampled using this particular equation, where you are writing mean and then standard deviation, and there is an epsilon. What is that epsilon term? Epsilon is sampled from, once again, a normal or a Gaussian distribution. Now again there is a randomness. Yes, there is a randomness, but that randomness is completely independent of those two terms. And during backpropagation, this is treated as a constant. And this is something which model need not have to learn, because it is totally independent, and those two parameters, mean and standard deviation, it is depending on the input x and then the parameters, that is weights and bias. I hope this is clear to us. If it is still not clear, let us proceed further, and then we will see that mathematically. So what we have done, random reparameterization trick is separating the randomness from the encoder parameter. Right? Definitely it is separated. Now this is how you are writing the equation. Now the gradients can flow from decoder back to the encoder. How? Let us look into this. Now can we able to, the entire problem was derivative of Z with respect to mean and derivative of Z with respect to sigma or standard deviation was something which was unknown for us from the previous one. Now why? Because Z was sampled using this. Now what we are doing, we have sampled Z in a different way, slightly we have by using reparameterization trick. So now this is the Z equation. Can we now differentiate with respect to mean? Yes, let us go ahead. Derivative of Z with respect to mean here. How is that you are writing? Derivative, this term is you are writing derivative with respect to mean, and this term also derivative with respect to mean here. Now since this is 1, definitely the value is 1, that is what is been written here. And in the second term, here you do not have any mean value. Since this term does not contain a mean, the derivative becomes 0. Therefore, can you write this whole equation as 1 plus 0? Why? The first term is 1 and the second term is 0. Why second term is 0? Because you do not have this particular does not have the term mean. Therefore, you now got a value. Earlier this was the problem, we were not knowing what exactly is the value for this, but now we got the value. Likewise, can we now compute with respect to sigma? So when we differentiate it with respect to this term, so here you do not have this, therefore this term becomes 0, and here you have this, therefore when you take the derivative you are going to get an epsilon value. Therefore this particular, earlier we did not had a value, but now we are having a value for both of these terms. Right? Now, I hope this is clear to us. Earlier the problem was we were not knowing the value of these two, but now we have a value for these two. Okay. Now, let us have a quick summary What is that we have discussed so far? The decoder is the one which is going to give us the output. So how is that it is going to give? Mathematically you are writing the output is denoted as x hat, and for that we are giving an input as a z, and this is an decoder neural network. Theta is the parameters, and you can easily update those parameters. Okay, then so decoder is not an issue. From decoder we have now reached to z. The loss depends on z through x hat. We have seen that. So which means how is that you are writing derivative of loss with respect to z is with respect to x hat and x hat with respect to z. This is also not an issue. Now later, using a reparameterization trick, z is being sampled. How is that z you are obtaining? Z is obtained in this way. Now because you have written in this, just some time back we have seen that now definitely z is differentiable with respect to both of these parameters. Because of this we got this value as 1, and here with respect to this we got an epsilon value. Okay, so which means what was the problem earlier, we were able to solve this particular problem. So what is that we have done? So once the gradient reaches the latent space z, we must now the gradient has to go back to the encoder outputs. What are encoder outputs? Mean and then the standard deviation. Yes, we are able to reach to this point. How is that we are able to reach? From from loss we are reaching to x hat, from x hat to z, from z we are reaching to this. So is it not for mean, this is the path, and how is that using a chain rule you can write? Is it not using a chain rule? Derivative of loss with respect to mean is loss with respect to x hat with respect to z, and z with respect to this. We have a value for each of these. This particular term value is 1. So if this value is 1, then definitely derivative of loss with respect to mean, is it not this? So is it not we can easily compute? Yes. So similar way, this is how we will compute with respect to a standard deviation. So from this, how can you reach to this particular one? This is the path. Loss, from loss you will reach to x hat, from x hat you will take the derivative with respect to z, and from z with respect to the standard deviation. So sometime back we have seen the value is epsilon. So we have got the value. So which means from loss you have reached to decoder, from decoder you have reached to z, from z you are successful reaching to the output parameters. What is only left out? You have to now go to the encoder, and in the encoder also we have weights and bias. We have to now reach there. So what is the next step? Finally, after once the gradients has reached the encoder output, that is the mean and then the standard deviation, we can now propagate to the encoder parameters. From can you visualize this? From x hat we have now reached to an decoder. From decoder we have reached to a latent space. From latent space we have reached to these. Now we have to go to an encoder parameters. So that is what now the gradients has to reach to an encoder parameters. We can easily do that using a standard back propagation. What is the path? First of all, you have to reach to this parameter. Here 5 is an parameters of encoder, which will be weights and bias. So how can you reach this using an chain rule? Mathematically can we write derivative of loss with respect to mean, and from mean we can reach to this particular parameter. And how is that you are writing this? That is this particular term, right? So now we can easily update the parameters. So therefore the reparameterization trick enables us to find out the gradients from the output layer, and you can go back till the input, that is the encoder parameters. So with this you can able to compute the gradients, and end-to-end training is possible in VAE. So this is all about the reparameterization trick. So far we have never seen the complete architecture of VAE. We had seen in bits by bits. So this is what is the complete architecture of VAE. We have an input X that is passed to an probabilistic encoder, and the encoder is something which is going to give us this output. And how is that we are sampling Z? Z is being sampled by using this mean and then this term, and then we are using an term epsilon. Epsilon is also being added. And this Z, once you get Z, Z is then passed to an decoder, and the decoder is going to give us the output, or it is X hat or X dash. This is what is the overall architecture. And what we have discussed in this particular session is reparameterization trick, right? So before reparameterization, Z was sampled from this particular distribution. After reparameterization, Z is obtained from this particular equation. This is the equation through which the Z is obtained. Because of this, Z is differentiable with respect to those parameters. With this, we have come to an end of this particular session. So far we have seen the detailed architecture of encoder, decoder, and then we have seen the most important concept now called reparameterization trick. In the coming session, we will understand the entire working mechanism of VAE by solving one numerical example, so that the overall flow will be very clear. With this, thank you.